All right, hello everybody, welcome back to another video. And in this video, we're going to be taking a look at a question from the IB Chemistry Paper 1 HL from the May 2018 Time Zone 2 batch. Now, this is a Born-Haber cycle question, and I know that majority of students find this topic absolutely horrendous, and me, myself included, I absolutely disliked Born-Haber cycle because I never understood it. I don't know what the purpose was. I had no idea what these fancy arrows and these diagrams were, but I am hopefully here to now clear your confusion about this topic because my teacher, the person who taught me, did a very good job at simplifying this concept for me. And then I realized how easy it actually is. And I'm hopefully going to be able to simplify this for you. And together we can find the answer to this question. And alongside that, I'm also going to explain the Born-Haber cycle to you and what these different enthalpies, these different numbers, arrows, what does this mean? What on earth is lattice enthalpy? What are these definitions, right? I'm gonna tell all of it to you in this video. Now, one thing that you should know, this is a question, or Born-Haber cycle is from topic 5, and topic 5 and the HL part of that as well, which is topic 15. So 5 and 15, both of them, it's all about definitions, right? My tutor told me this. It's all about definitions. You have to know the definitions if you want to be good, because there's so many definitions in this subject, or in this topic. You have things like lattice enthalpy, for example. You have enthalpy of combustion, enthalpy of formation, bond enthalpies, this, that. There's so many definitions, and you should know exactly what these definitions mean. Otherwise, you are going to face problems in the exam. So hopefully I'm going to be here to clear the definitions that are involved in Born-Haber cycle. First off, why do we create a Born-Haber cycle? What are we trying to calculate? The main purpose of creating a Born-Haber cycle is to calculate the lattice enthalpy over here. This is what we calculate. And don't be tricked or don't be confused by this form of a diagram. This diagram, this whole thing is nothing but another variant or another version of a Hess's cycle. This is basically a Hess's cycle, right? Because what do we do in a Hess's cycle? Yeah, we use an alternative pathway. So suppose we want to get from A to B, we want to figure out the enthalpy change of the reaction from A to B. But we don't know what the enthalpy change is, but we can use an indirect pathway where we convert A into C. So we know the enthalpy for this example is 5. And then we convert C into B, and we know, for example, the enthalpy of this, which is 6. And we just add 5 plus 6, 11. And that is also the enthalpy change over here. So that's basically what Hess's law says, right? Hess's law says that it doesn't matter which direction or which pathway you use to get to your final product, the enthalpy change will be the same. That's basically what, in very simple baby terms, that's what Hess's law says. It doesn't matter. And this is the exact same thing. We're trying to find what enthalpy change is, what lattice enthalpy is, which is also a type of enthalpy change. But we don't know what this is directly, so we're using other types of enthalpies to find out. And now, why do we use this Born-Haber cycle? Mainly because in a regular Hesse cycle like this, if you notice, really the maximum number of enthalpies we can use to calculate this over here is only 2, right? You can use one type of enthalpy over here, and you can use one type of enthalpy over here. After that, it starts to get a bit confusing, isn't it, right? If you seem to add more. So suppose if I do something like this, right? If I do C to D, D to E, and then I take it to B, that's confusing. That's pretty confusing. It gets really messy over here, right? So that's why this Born-Haber cycle makes it so much simpler to use numerous types of enthalpies to get the final value. Yeah. In a normal enthalpy cycle, that I would show over here, we would probably just use 2 enthalpies, right? For example, we could use enthalpy of combustion. No, actually, that's a bad example. We could use, I don't know, we can use lattice enthalpy, and then we can use enthalpy of hydration, right? Then we have these 2 enthalpies over here. That's it. But over here, to calculate the lattice enthalpies, unfortunately, we need a lot more enthalpies, a lot different types of enthalpies, not only 2, right? So we first need enthalpy of formation. This is the first thing, enthalpy of formation. So this number, negative 829, represents enthalpy of formation. Then this positive 164, if you notice in this reaction, strontium, which is the chemical over here, which is Sr, is being turned into gaseous. And this reaction, whereas chlorine, it remains the same, right? It's Cl2 gas and it's Cl2 gas in both these places. But strontium is being turned into a gas. And this reaction to turn strontium from solid into gas has an enthalpy change of positive 164, which means it's endothermic, which is irrelevant for this, but just a quick side note. But this positive 164, this enthalpy change is called enthalpy of atomization. Now, what is enthalpy of atomization? Because remember, a lot of definitions. So I'm going to tell you what enthalpy of atomization is. Basically, enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from an element under standard conditions. And as you can see, we are forming 1 mole of gaseous atoms from the element in its standard conditions. Now, they haven't told you that the conditions are standard over here, but we just assume that it is, right? Just have to assume that it is, because that's the only way that we can calculate what enthalpy of atomization is. And they've given you the enthalpy of atomization, it's 164, right? So that's enthalpy of atomization. Remember, I'm going to repeat this once more. Enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from an element under standard conditions. So we're forming 1 mole of gaseous strontium atoms from solid strontium atoms. Now, let's take a look at the next one. Positive 243. In this case, we see that Cl2 becomes 2Cl. Now remember, this Cl2 and 2Cl are not the same thing, right? This is not the same. Cl2Cl refers to two individual chlorine atoms, which are not bonded. There's no bonding between them. Whereas Cl2 refers to chlorine atoms bonded together by a single covalent bond. But 2Cl refers to two individual chlorine atoms, right? And this is also an enthalpy of atomization. This is also an enthalpy of atomization, because we are breaking down whatever this bond over here is, and we are getting 2 moles of chlorine gas, of individual chlorine atoms. And now you might be a bit confused, because earlier to you, I mentioned that enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from an element under standard conditions. However, in this case, it's 200, we are forming 2 moles of chlorine gas at which kind of goes against the definition, right? But actually, the matter of fact is the enthalpy of atomization is still the same. Right? It's still the same, whether it is 2Cl or whether it's 3Cl or 4Cl. Enthalpy of atomization is the same. We have just multiplied it by 2, because now we're forming 2 moles of chlorine. So if we do 243 divided by 2, we're going to get some fancy looking decimal. Yeah, we're going to 121.5. So this would be the enthalpy of atomization for chlorine. But since we are forming 2Cl, we just multiply this by 2, and then we get the enthalpy of atomization for this specific reaction. Anyways, let's continue. Now, what is this? Positive 550. What enthalpy is this? And let's see what has changed between these two. Well, we can see that Sr has a small plus sign. That means that Sr has given off 1 electron and has formed a positive ion, right? Because that's the only way that it can get a plus sign. And that this reaction here, where Sr ionizes or it forms an ion, is called first ionization energy, right? And what does this mean? Basically, the first ionization energy is the enthalpy change when 1 electron is removed from every single atom in 1 mole of gaseous atoms. So, in very simple terms, basically, the enthalpy change when 1 mole of electrons is removed from 1 mole of gaseous atoms under standard conditions. That is basically what first ionization energy is. Now, hopefully you are beginning to see things tie in, right? Because let's see, we first converted strontium from solid into gaseous. and now we are ionizing it. What is the purpose of this atomization? Well, you can see it. First ionization energy can only be calculated for gaseous atoms. So that's why it was essential to convert this solid into gas. Otherwise, we would have not been able to calculate its ionization energy. But we did that, so we can. That's why we have the privilege of doing that. So this is the first ionization energy. I'm just going to refer to this as FIE. Okay. Now, what is this? Oh, that's a big enthalpy change, positive 1064. What has changed? Well, let's see. Strontium has become 2 plus. That means that Sr plus has now become Sr2 plus E minus. So it has now given away 2 electrons to become Sr2 plus, right? And that's a big change in enthalpy. This requires a lot more energy. It takes a lot more energy to remove another electron from strontium. Well, what is second ionization energy? It's the exact same thing. Second ionization energy is the enthalpy change to remove 1 mole of electrons from 1 mole of gaseous positive ions. And well, we have gaseous positive ions, and they've removed 1 mole of electrons from them. And there we go. You have your second ionization energy. So strontium has formed 2 plus. Now we have gathered these electrons, right? We have these electrons, yet strontium has given off 2 electrons. What do we do with these electrons? Well, we're going to add it to the chlorine, because remember, 2Cl is nothing but Cl atoms and Cl atoms, right? It's 2 chlorine atoms. And as you know, chlorine has a valency of 7. So it has 7 electrons. And we have 2 of these chlorine atoms. And hopefully you're beginning to see the picture now. Now these 2 electrons, one is going to be added to here, and another one is going to be added to here. And there we go. We have 2 chlorine ions. We have formed 2 chlorine ions. And that's exactly what's happening over here. Negative 698 is the first electron affinity of chlorine. And first electron affinity of chlorine is the enthalpy change when 1 electron is added to each atom in 1 mole of gaseous atoms. Basically, electron affinity is the enthalpy change when 1 mole of electrons is added to 1 mole of gaseous atoms. That is the exact same thing. And in this case, since we have 2 moles of chlorine, we have multiplied the enthalpy change of, or the first electron affinity of Cl by 2. And you can calculate what the electron affinity of chlorine is. Just divide negative 698 by 2 if you would like to find out, but that's really irrelevant to this question. It doesn't matter. So that is the first electron affinity. So at the end of the whole process, we have formed Sr2 plus and we have formed 2Cl minus. And hopefully you're beginning to see everything tie in, right? So second ionization energy, and this is first electron affinity, right? Hopefully you're beginning to see everything tie in. And this final piece of terminology, or the definition I'm going to tell you, will hopefully make everything much more clear. What is lattice enthalpy? Why are we doing this? Lattice enthalpy is the enthalpy change when 1 mole of an ionic compound is broken apart into its constituent gaseous ions under standard conditions. And that is exactly what we have done here. We have broken apart a ionic compound. This is an ionic compound, and we have broken it apart into its constituent gaseous ions, right? We have formed the ions under gaseous conditions, and this is basically the whole process. It's step by step, right? It's like a recipe. The first thing you do, you first atomize both the atoms in the compound. You atomize Sr, you atomize chlorine, then you remove the electrons from the positive ion, right, which would be Sr in this case. You remove the electrons. That's first ionization energy. If you need 2 electrons, remove another electron. That would be second ionization energy. And now that you have the electrons, add it into the chlorine, right? That's first electron affinity. And perhaps in another example, if you need more than 1 electron, or if you have or if your ion, or if your negative ion requires 2 electrons, then you can also add the second electron affinity. right? That is the recipe. You can think of it like a recipe. Now, how do we calculate lattice enthalpy? Now, what's the final stage? That is what this question is all about, right? I've gone through all of the process of Born-Haber cycle, what it is, what it's doing. I've explained everything, but what is the final goal? How do you calculate finally what the lattice enthalpy is? Well, I'm going to show you how to do that as well. It's very, very simple. I'm going to erase all of this so that I can make things a bit more easy to understand. So if you haven't done it yet, please rewind and take a screenshot or something like that, and hopefully that will help you. Now, how do you calculate this? How do you calculate the final? What is lattice enthalpy? Because we know that in the enthalpy or in the Hess's energy cycle, it's pretty easy to calculate. But how do you do it over here? Basically, in order to calculate, remember one thing. All the arrows that are going clockwise, all the values on the arrows that are going clockwise should be equal to all the arrows or all the values on the arrows that are going anti-clockwise. Now, what do I mean by that? Look at a clock, right? I'm just going to draw a clock over here. What is the clockwise direction? What is the clockwise? Clockwise direction is this way, right? That's how we go from a clock. And anti-clockwise would naturally be this way. Now in this thing, imagine this whole thing is a clock. I'm gonna act like it's a clock. I'm gonna draw a big circle around it. There we go. So this is a clock. What would be the clockwise direction? Well, the clockwise direction would be this way, and the anti-clockwise direction would be this way. Now, which are the clockwise arrows? Well, or the clockwise values? This one, this one, this one, this one, and this one, because it's all going clockwise. And which are the anti-clockwise values? This one, and well, only lattice enthalpy. Now, in order to calculate lattice enthalpy, I'm just going to name this variable as x because we don't know what it is. And what we do know is that clockwise values should equal to anti-clockwise values. So in simpler terms, 164 plus 243 plus 550 plus 1064 minus 698, because this value over here, sorry, this value over here, minus 698 should equal to negative 829 plus x, because that is lattice enthalpy. And why is it positive? Well, because the arrow is going upwards. That means it's an endothermic reaction, and that means that the enthalpy is positive, right? So, well, all we have to do is isolate x, and that's simple. Just take this over to the other side. So it will be 164 plus 243 plus 550 plus 1064 minus 698 plus 829. Now, which of our answers in this MCQ, which matches it? Let's see. No, not this, because we have this plus over here. That doesn't make any sense. Not this, because we have a minus 829. That doesn't make sense because in our answer we have a plus 829. What about C? Well, okay, we have a plus here because remember minus and minus make a plus. We have and we have a minus. Yep, this is the correct answer. This is the correct answer. And that's it. That's how we have done it. Hopefully I've gone through and I've explained the Born-Haber cycle well to you. Thank you so much for tuning into this video. I will see you in another video with another question. And before we go, to all those who are still a bit confused or are confused about any other topic, please feel free to message me on my social media, send me an email or put it down in the comments below and I'll be more than happy to help you. Thank you for watching. I'll see you in another video with another question.